We began this course with the study of Coulomb's law, which is a force of attraction or repulsion between charges. There are two types of charges, opposite, positive and negative, and the force can be either attractive or repulsive. If the charges are the same, the force is repulsive. If the charges are opposite, then the force is attractive. So in this particular problem, we're asked to calculate the electrostatic force between the two, and the equation that we use is right over here, where Q1 is the charge on one of the charges, and Q2 is the charge on the other charges, and R is the distance between them. And so just putting in K here is a constant called Coulomb's constant. So putting in the numbers, we can calculate the force of attraction or repulsion between the two charges. In this case, the charges are the same, so they repel one another. So on the charge on the left, the force will be toward the left, and on charge on the right, it will be towards the right. Those forces will be equal and opposite. Typical problem you can get with maybe one like this. Let's assume that the force between these two charges is F. What would the force be if we move the charge B from point B and put it over here at point A, or 1/2 the distance? Originally the distance was R, and now it's going to be half of that. Well, we know that the force is proportional to 1 over the distance squared, right? So if we move the charge, there'll be a new force, and in this case, since the distance is 1/2, it'll be 1/2 R squared. So 1/2 R squared is equal to 1 over 1/4 R squared. And this is 4. 1 divided by 1/4 is 4. 1 over R squared. So originally it was 1 over R squared. Now it's 4 times that. So this would be the correct answer. In this particular problem, type of problem you may get on the test is just to calculate the value of the force, like the previous one, using these numbers. Like Q1 is 6 microcoulombs, or 6 times 10 to the minus 6 coulombs, and 2 is minus 4 microcoulombs. So in this case, the force would be attractive between them. We also introduced the concept of an electric field. We know that if you have two charges, say Q1 and Q2 as I have here, there's a force between them, either attractive or repulsion. But what if I remove one of the charges? What, if anything, is there at this point where the charge used to be? Well, we say there is an electric field there, defined as the number of coulombs of force, a number of newtons of force that 1 coulomb of charge would experience at that point. So this would be the electric field. Its units are newtons per coulomb. And if you take this divided by Q, you get this equation, that the electric field due to a point charge is given by that equation. In other words, there's no other charge here. Now, if you move the charge through this electric field, you need to do work because you have to exert a force. And we define the potential difference between 2 points A and B, say moving the charge from A to B or from B to A. The potential difference is the amount of work we have to do to move 1 coulomb of charge, or the work per coulomb. Now, since electric field is defined as number of newtons per coulomb, F is equal to QE from that equation, and work is equal to force times distance. So it would be QE times delta x, or x. per Coulomb, so the Q's cancel here, and you see that the work done in moving a charge from point A to B is equal to the electric field between A and B if the electric field is constant times the distance. Now, in the case of a point charge, the potential difference is given by this equation, and this represents how much work would need to be done to bring a charge in from infinity and place it here. To bring 1 Coulomb of charge from infinity and place it at this point, the amount of work that you would need to do is given by that equation right here. We can apply this a little more readily to situations where the electric field is constant. That occurs if we have something like 2 conducting plates that have equal and opposite charge on them. So one plate here has a positive charge, the other plate has negative charge. Identical amount of charge. That means in the area between the plates there is an electric field, and it's constant. As you go from one point to the other, electric field stays constant. That means if you place a charge, like this charge Q over here, into the electric field, it will experience a force equal to QE. And therefore, if I move a charge from one plate to the other, I have to do work. The potential difference is defined the amount of work that I have to do to move the charge per Coulomb, to move the charge from one plate to another. So a volt is defined as how many joules per Coulomb. Since we're going to replace delta X with just the plate separation D, then the work, or the potential difference across the plates, is equal to the electric field in between the plates times the separation of the plates. Now again, if you do work to bring a charge from infinity and place it next to a point charge, the amount of work you did from the definition of voltage is equal to that. Or we can use this equation here. This is only for point charges. So let's see what kind of problems you can get in this. How strong in volts per meter is electric field between 2 metal plates 25 centimeters apart if the potential difference between them is 100 volts? So we have 2 plates. There's a potential difference between them of 100 volts. And we know that the potential difference across the plates is equal to E times the plate separation. Call that delta X or D. So here you just use those numbers. They are 25 centimeters apart, so that's D, that's delta X, but we have to put in 0.25, it change to meters, everything. How strong is the electric field? E is what we're looking for, and the plate separation is 100 volts. So if you solve this for E, you get E is equal to 400 volts per meter. Here's another problem utilizing more or less the same equation. Here you're given the electric field between the plates, given the plate separation, but in millimeters. So this is 4 times 10 to the minus 3 meters. And you're asked to find the voltage. Same equation. The voltage is equal to the electric field multiplied by the plate separation. The electric field is 3.5 times 10 to the third, 3,500. And you got to multiply that by delta X, which is 4 times 10 to the minus 3. And so when you do that, you get C is the right answer. third type of problem using this. We're using the fact that the amount of work we have to do to move a charge from one plate to the other, a charge Q, is equal to the amount of joules per coulomb, which is delta V, multiplied by the number of coulombs that we're actually moving. So in this case, you're asked how much work in joules is done by a uniform field. So the work is also equal to force times distance. And the force is equal to QE times distance. And so this is the equation we're going to use. Q is equal to 6 microcoulombs. This is Q in that equation. E is 300 newtons per coulomb. This is E in that equation. And delta X is 20 centimeters or 0.2 meters. Putting all those numbers here, you should come out with that answer. As a final problem, we're going to use the fact that voltage is defined as the number of joules of work per coulomb we have to do. This is the definition of voltage. How many joules of work to move it from point A to point B. So what is the potential difference between 2 points in an electric field if 1 joule of work is required to move 1 coulomb of charge? That means we do just 1 joule in order to move 1 coulomb of charge. So it's 1 joule per coulomb, which is the answer. If we did more than one, say if we did 2 joules of work to move 1 coulomb of charge, then of course the answer would be that.